We often employ artificial neural networks to encode data. These networks dives into the data, uncovering complex patterns and hidden associations. But how can we manage this process? Let's presume we have a neural network which produces a specific result based on input data. In our case, we want the network to produce the output of 1. Knowing the output enables us to calculate the difference between the actual output and the expected value. This gives us a measurable indicator of how close we are to reaching our goal. However, modifying the weight at random produces the random outputs. Thus, we need to establish a robust training algorithm which will allow us to converge successfully. But how do we go about measuring the error value for the neural network? Our first option is to calculate the difference between the actual output and the target. However, the resulting graphical representation is not very useful. It's challenging to point to the value closest to 0. Let's opt for the mean squared error, also known as MSE, as the new measure to test out. Now it's evident when we have reached the lowest error rate. Moving forward, we will opt to use MSE as our preferred loss function. Imagine a scenario where we are familiar with the loss plot. Looking at this plot pointing to the minimum is not a big challenge. We can either manually identify the minimum or use a derivative to find it. However, we usually don't know the loss plot. We can only hypothesize if we have landed to the global minimum by analyzing numerous loss values empirically. One possible methodology would be employing a Monte Carlo simulation, initiating the weight selection process at random. This method will be useful if we are measuring the impact of a single neuron to the total loss plot. In reality, we usually have millions of neurons or even more to manage. This again calls for a robust algorithm capable of identifying the minimum within multidimensional and highly complex surfaces. Let's review the concept of derivatives that we will often use in our calculations. When we calculate the derivative of a function, the result informs us about the speed at which the function changes at the given step. The value is negative and is maximum at the steeper descent of the hill. The value approaches or stops at 0 when the function hits a plateau. The value is positive and maximum when the function is growing rapidly. With that in mind, let's go back to the original goal of searching the global minimum. For this, we will utilize the gradient descent algorithm. Think of gradient descent as an algorithm for training neurons and minimizing the error outputs. The main objective of the algorithm is to identify the loss function output's global minimum. The core concept behind this algorithm is to calculate the derivative and then decide our next step based on the result. Let's get started with the predetermined step size. As we can see, our progress was halted at the local minimum, and then we went back and forth, failing to reach the minimum. Let's try altering the step size and see if we are in luck this time. We made a better progress this time, but the result is still not optimal. We didn't even manage to reach the local minimum. Now, we will introduce the concept of a learning rate, making our step size dynamic and reliant on the learning rate value. In this case, the learning rate is set at 0.1. Generally, the step size is also dependent on the neuron output value, but since we are trying to minimize a single neuron's value, we can bypass this and simplify our calculations. Let's strive to find the minimum once more. The situation has improved significantly, but we still haven't achieved the minimum value. Next, we will integrate a decay function that will gradually decrease our step size. Let's continue the algorithm incorporating the decay function. This time around, we managed to reach the minimum. Although it's not a global minimum, the result is still optimal. The gradient descent algorithm does not provide a fail-safe guarantee that we will reach the global minimum. If we aim to reach it, the simplest course of action is to try different seed values. This illustrates why it's so vital to have a fixed seed value. Without a fixed seed value, replicating the experiment will be impossible. Using a different seed value yields a different starting point and result for us. In this attempt, we've managed to reach only a local minimum. We will have another go. Congratulations, we have finally reached the global minimum. We have accomplished calculating the neuron's output. Next, we pass the result to the loss function. This provides us an error value, showing how the output diverges from the expected value. The challenge now lies in the complexity of the neural network. It contains many layers of neurons. We will solve this by implementing the backpropagation algorithm, which will propagate the error backward through all the layers. To begin, it's important to grasp the chain rule. This fundamental derivative rule forms the backbone of the backpropagation algorithm. We will illustrate the concept of the rule through a hypothetical system where the car speed has a linear relationship with the bicycle speed, which in turn depends on the man's walking speed. Applying the chain rule, we can recognize the impact of changing the input, meaning the man's speed, on the output unit, meaning the car's speed. Now imagine we reversed the scenario. Suppose we know the desired car speed and we want to maintain the balance in the system. Keeping this in mind, we will propagate the difference back. But how can we achieve that? We will utilize the chain rule and reverse it. In order to do this, we will calculate the derivative of the inverse function. Fortunately, the linear function has an inverse. We just have to invert the fraction. After getting this relationship, we can multiply it by the car speed difference to determine the speed difference for the man. How do we apply the chain rule to the neural network? The neural network layer could be represented as a simple function or neuron. Then we stack more layers, allowing the neural network to capture more knowledge and uncover a relationship within the data. In essence, every layer relies on the previous layer, similar to our man and car system. At the bottom, there is a mathematical representation of the neural network. You might think this neural network is overly simplified. Most real-world applications demand much more complex networks with multiple neurons at every layer. However, the presence of multiple neurons merely complicates things more than necessary. To illustrate more clearly, let's reimagine this with multiple neurons within a layer. Now the equation looks more intimidating, and unraveling the relationship calculations will require significant effort. However, whether it's a primitive network or a complex one, the key concept remains the same. Thus, for our purposes, we will approximate multiple function sums with a single function. Let's return to our flat neural network. Next, we will apply the chain rule to our neural network. We have an input x, which passes through our neural network. This input gets multiplied by the neuron's weight. Subsequently, we add the neuron's bias. Lastly, we apply the activation function, thereby obtaining the neuron's output. Let's add another neuron to act as the output neuron. We will propagate the input through the neural network. Now we have successfully obtained the output value. Using the chain rule, we are capturing how modifying the input will affect the output. To simplify the equation slightly, we will introduce a new variable v representing the neuron's output value. We will also have another application for this variable. After obtaining the output, we compare it to the target, giving us the difference or error value. However, positive output values from the loss function only serves as an illustrative measures for reviewing the training process. In order to update the network weight, it's essential to know whether the error was positive or negative. Therefore, we will be using the loss function derivative to determine the error's direction. Next, we must propagate the error backward through the network. But you might ask, how do we do that if for the man-car system we used a derivative of the inverse function? Indeed, linear functions have their inverses. But what about nonlinear activation functions? Not all activation functions have their inverses. For example, the ReLU does not have an inverse function, while the sigmoid does. To apply the chain rule and propagate the error backward, we will employ a little hack, which is used in most popular libraries as well. During the feed-forward process, we calculate the neuron output and persist it in variable v, and only then we pass it to the activation function. During backpropagation, we won't need to recalculate the initial output. It's already available in memory. This means we don't need an inverse function. We simply take the original output value and feed it to the activation function's derivative to get the relation rate for propagating the error back through the network. Now we can start propagating the error back. For the next layer, the error calculation will reuse the stored neuron outputs and its relation rate with the previous layer. We can continue to propagate further by multiplying the relation rate and the next layer's weight. The same calculation holds true for the real neural networks with additional layers and numerous neurons in each layer. First, we determine the error value for the output layer. Then, we propagate it backward through the network. Let's have a brief recap of the key points what we've touched on today. Firstly, the process starts by passing the input through the neural network. Subsequently, we utilize the loss function to calculate the error and save the value as a measure of the neural network's performance. Afterwards, we calculate the error derivative for the weights update phase. Subsequently, we propagate the error back through the network, calculating an error value for all layers. Lastly, we can update the neural network's weights. These stages make up a single iteration of the neural network's training process. However, in reality, there are thousands of such iterations. Fortunately, there are libraries that manage all these calculations. One of the first libraries was Autograd, which is now abandoned in favor of JAX. The other popular frameworks, such as PyTorch and TensorFlow, also provide this functionality by default. Thank you for your attention.